Thanks to my Patreon members for supporting this channel. You can support this channel by going to my Patreon page. Link is in the description below. Now back to the video.
Researchers in the Hong Kong University released a new AI paper titled Large Motion Video Autoencoding with Cross-Model Video Variational Autoencoder. Video processing is at the forefront of machine learning advancements, enabling applications such as efficient video streaming, editing, and generation. A key challenge in video processing is to develop techniques that can encode and decode videos while maintaining high fidelity, even in cases involving complex motion or significant scene dynamics. The use of variational autoencoders, VAS for video processing, has gained traction because of their ability to generate compact, latent representations of videos, which are crucial for applications like video compression and video generation. While image VAS are well established, applying them directly to videos often results in significant shortcomings. Frame-by-frame processing fails to account for temporal dependencies between video frames, leading to issues like temporal inconsistencies and motion artifacts. To address these challenges, researchers have explored video VAS that aim to compress both spatial and temporal information. However, current approaches often struggle with reconstruction quality, resulting in motion blur, temporal flickering, and loss of detail. In response to these challenges, the paper Large Motion Video Autoencoding with Cross-Model Video VAS introduces a novel and highly effective video VAS architecture. This new approach emphasizes robust spatiotemporal modeling, cross-model integration with textual data, and joint training on both images and videos. This essay explores the core ideas, innovations, and contributions of this work in a manner accessible to both experts and lay readers. To understand the significance of this work, first delve into the challenges of video VAS. Traditional image VAS, such as those used in Stable Diffusion, excel at compressing spatial details in individual frames. However, videos are not merely sequences of independent frames. Videos include temporal information, the changes from one frame to the next that convey motion and continuity. Ignoring this temporal aspect results in two major issues: temporal flickering. When each frame is processed independently, there is no guarantee that the encoded frames will align smoothly in sequence, causing flickering. Inefficient compression. Videos often contain significant redundancy along the temporal dimension. For instance, static backgrounds or slow-moving objects do not change much from frame to frame. Without temporal compression, this redundancy is not effectively reduced. Existing solutions attempt to address these problems by incorporating temporal compression. However, these methods often introduce new artifacts such as motion blur and detail distortion, particularly in scenarios with large or complex motion. The paper proposes a groundbreaking video VAS architecture designed to overcome the limitations of existing models. Approach consists of three key innovations. 1. Temporal-aware spatial compression. The authors recognize that simply extending image VAS to the video domain by employing 3D convolutional networks is insufficient. 3D convolutions allow simultaneous spatial and temporal compression. They often lead to blurring and loss of fine details. To address this, the authors propose a novel temporal-aware spatial compression method that decouples spatial and temporal encoding processes. The architecture uses a combination of simultaneous and sequential spatiotemporal compression to leverage the strengths of both approaches. Simultaneous compression captures low-level temporal smoothness and texture stability. Sequential compression enhances motion recovery and temporal coherence, particularly for scenarios involving large motion. These methods, the proposed model achieves better overall reconstruction quality, preserving both spatial details and temporal consistency. One of the most innovative aspects of this work is the incorporation of textual information into the video encoding and decoding process. Datasets where video frames are paired with descriptive text captions provide a rich source of semantic information. The model leverages this text guidance through cross-modal learning, text-conditioned encoding and decoding. During encoding, Text descriptions guide the spatial and temporal compression processes. During decoding, textual cues help reconstruct fine-grained details and maintain semantic consistency. By incorporating text guidance, the model significantly improves reconstruction quality, especially for videos with intricate details or complex dynamics. Another major contribution of the paper is the joint training approach. The model is designed to process both images and videos, making it versatile and efficient. During training, image batches, only the special modules of the network are activated, skipping temporal modules. Video batches, both spatial and temporal modules, are utilized, enabling the model to learn temporal dependencies. This joint training strategy offers several benefits: enhanced reconstruction quality for both images and videos, improved model versatility allowing it to perform both image and video autoencoding, more efficient utilization of available datasets, as image datasets are often larger and more diverse than video datasets. The proposed architecture includes a temporal-aware spatial autoencoder that extends pre-trained image phase into the video domain. Key components include Splunk thread combines expanded thread convolutions with additional temporal convolutions to achieve spatio-temporal compression. Cross-attention layers facilitate cross-modal learning by integrating textual conditions into the encoding and decoding processes. Vectorized design ensures modular processing of spatial and temporal information, supporting joint training on images and videos. The model's spatiotemporal design enables it to handle complex video dynamics, while the cross-modal capabilities enhance its ability to preserve fine details and semantic consistency. The effectiveness of the proposed DAOV is demonstrated through extensive evaluations on challenging datasets. Key findings include reconstruction quality. The model outperforms state-of-the-art baselines in preserving spatial details, temporal coherence, and overall fidelity. Modeling. The temporal-aware spatial compression approach significantly reduces motion blur and stuttering, enabling smooth and accurate motion reconstruction. Versatility. Joint training approach allows the model to perform both image and video autoencoding with superior performance in both tasks. Cross-modal benefits. Text guidance improves detail preservation and semantic alignment, particularly in complex or dynamic scenes. DAOV that sets a new standard for high-fidelity video compression and autoencoding. By addressing the limitations of existing methods, the proposed approach achieves remarkable improvements in motion modeling, temporal consistency, and detail preservation. The integration of cross-modal learning without textual data and the joint training on images and videos further enhances the model's versatility and reconstruction quality. This work not only advances the state-of-the-art in video processing, but also opens new avenues for cross-model learning and multitask training in machine learning. Its implications extend to various applications, including video generation, streaming, and editing, making it a valuable contribution to the field. Thanks for watching, and I will see you in the next video.